Cool. All right. It's 2:05, so I figure we should start. Thank you all for showing up. Hopefully a few more people trickle in as we start. So my name is Phoenix. I am the only INMM officer here right now. I am the secretary. I know our president and vice president both had their internet knocked out by the storm last night, so they could not make it. So thank you all for braving that. So yeah, welcome to INMM. Our first talk is going to be on Professor Carl Willis's search for Cosmos 954. It should be very interesting. And Carl, you can, decide if you want, people to ask questions during, or we can save that all for the end. That's all up to you. But without further ado, I say take it away.
All right. Well, thank you, Phoenix, and thanks for having me to INMM to talk about this fun little project. I should mention that I'm planning on doing a couple things that may challenge some people's bandwidth, and so we'll just have to sort of play it by ear. So one thing, of course, I'm using the relatively new Zoom feature, putting the slides behind me rather than sharing screen for the slides. It seems to work pretty well, but that may be sort of platform dependent. So we'll have to see how that works for you. If you run into trouble, use the chat feature. There's only, I think, 11 folks out there. So just if there's technical problems with what I'm doing, use the chat. Let me know, and I'll change the way I'm doing the Zoom thing. The other thing is I'm going to play a video later on. It's some video footage of pieces of this satellite at a museum in Yellowknife in Canada, and I took the footage. But again, Zoom has a feature for delivering video, and video always requires high bandwidth. And that'll probably, strain some resources. So we'll just have to see and play it by ear. But like all things these days, I'm open to changing what I'm doing and trying to make it more accessible. So anyway, a little about my background if you don't know who I am. I'm a faculty lecturer in the department, and I currently teach the Nuclear Engineering 101 class and also reactor operations and licensing for a select number of undergraduates. And I'm the chief reactor supervisor now for our little AGN 201M nuclear reactor on campus. So that's just my background. The title of this presentation is Searching for Cosmos 954. And so this somewhat cryptic title hopefully will become familiar to you afterwards, and you'll recognize the place of this particular episode in the context of space nuclear power. And so without further ado, we'll move along, and hopefully the PowerPoint will work out here. So the general context for what I'm going to talk about is space nuclear power accidents. And there are not very many of those, thankfully, but Cosmos 954 is one of them. So nuclear power obviously is attractive in space missions for a number of reasons. It can provide endurance that solar power or chemical batteries or fuel cannot. Especially in some power-intensive missions like the one we're about to talk about. It's also attractive for deep space missions where you're too far away from the sun to be able to get the power needed for the mission payloads. So obviously it's attractive as an enabling technology for a lot of space missions. But there is, of course, the question of what do you do if things go wrong? So specifically, what happens if nuclear reactors that are sent to space manage to find their way back to Earth, especially if they have experienced some significant burnup and have, a high core inventory of radionuclides? And then how do we protect people and the environment in the case of an accident? These are mass dispersal events, and they also involve the complexity of interactions with Earth's atmosphere, and then entrance into the biosphere, or possibly the hydrosphere, and where does that stuff go, and how long does it last, and sort of what is its environmental fate over the time intervals of days, weeks, years, months, and so forth. And then finally, we're going to look at some potential challenges with cleanup activities. In this case, technology is not value neutral, and the people who design these missions are not the only stakeholders. There are people, especially with space nuclear power, there are people all around the planet who could be impacted if something goes wrong, especially if it's an Earth orbiting mission. So basically anywhere on Earth could see the impacts. And so what are the cultural and geographical factors that affect how we might respond to this? So those are just some questions to keep in mind as I talk about the subject here. So here's the story of what happened. And we're talking about 40 plus years ago, back when a country called the Soviet Union existed, and no longer does. It's now broken up into its component republics. But back in the mid 1970s, there was this thing going on called the Cold War, which was a fairly steady escalation of military capabilities in an adversarial manner between the United States and its allied bloc and the Soviet Union and its allied bloc. And so this caused certain decisions to get made about what technology was deployed and how rapidly it was deployed, and what sort of relative consideration, safety and things like that were given. But the Soviet Union had a perceived military need to monitor ocean-going traffic from NATO countries. And so they came up with a concept to use a space-based radar. Well, radar is energy intensive, demands a lot of power to run a klystron to power the radar and get a signal, not just from the radar, but back up to the satellite and receive it. And then, of course, you have to do something with that signal, send it back to ground. So they came up with a design that used a nuclear reactor to power this mission. And Cosmos 954 was one of about 30 some missions of this type that they flew. They launched it from Baikonur, the Cosmodrome in Kazakhstan, which is still in use. And a few months later, NORAD in the United States identified that the orbit was unstable. This was classified information in the United States at the time, so the US didn't go broadcasting to the world, hey, there's a nuclear-powered satellite that's about to deorbit somewhere. The US kept it to themselves with the intention of, if it landed over land, we wanted to be involved because we wanted the intelligence. We wanted to learn what this space reactor was doing and what it was, how it was built, and so forth. So there was a secrecy and an intelligence prerogative from the standpoint of the U.S. military, but we knew that something was going on with this particular satellite. So in late January of 1978, it crashed in Canada, and telescopes in Hawaii picked it up and were able to, at that point, say that on that current mission, it was going to crash. The onboard reactor disintegrated, and contamination was spread pretty far and wide. And then the U.S. declassified what they knew to Canada because this crash had occurred in northern Canada. And the U.S. and Canadian government began a joint program called Operation Morning Light to recover as much of the satellite as they could and make the areas that were contaminated by the accident safe for human habitation. So what was the radiological risk they were dealing with? Well, some pieces of this reactor were extremely radioactive and measured about 500 rem per hour on contact. And as you know, that's pretty high. That's definitely enough to give you radiation burns, probably if you were close to it, and cause some, deterministic radiation injuries, possibly even acute radiation syndrome if you're around it long enough. So there's an acute hazard associated with these pieces. Beyond that, of course, there's also a long-term environmental impact, and that remains sort of to be understood, I think. But so Operation Morning Light recovered some of this satellite, And as we'll talk about, this was about a school bus sized thing weighing a couple thousand kilograms, and about 1% was recovered. So where's the rest of it? Well, it's in two places. Some ended up in the atmosphere during reentry, and presumably most of it is down on the ground, but we just don't know where it is and haven't found it. So that is the backstory of Cosmos 954 specifically. So where is this debris field? Well, if you look at a Google map and just keep scrolling north, basically from where we are in Albuquerque all the way up north through the Mountain Time Zone into Canada, into Alberta, and then if you keep going further north into the Northwest Territories, you pass Lake Athabasca, and then finally you come to Great Slave Lake, which is it's just a vast freshwater inland lake. Great Slave Lake is really at the center of the Northwest Territories. The capital is Yellowknife, which is up on the north arm of Great Slave Lake and has a population of about 20,000 people. And that's more than half of the population of the entire Northwest Territories of Canada. So the trajectory of this satellite was over the Great Slave Lake, mostly over the east arm, and then there was some wind blown, some wind driving the trajectories of debris down into a little further south of where the satellite trajectory was. So you have this span of almost 600 kilometers over which pieces of the satellite rained down. And as I mentioned, this happened in January, and this is north of 60 degrees north. So we are talking about an Arctic situation, the middle of winter. And so Operation Morning Light was more than anything a test of the military's capabilities of operating in such an extreme climate. So they had fixed wing aircraft and helicopters, and as well as dog sled teams deployed to help find pieces of this thing. And they're carrying scintillation survey meters. And the individuals, the people who were carrying these, had to put the survey meters under their layers of clothing in order to keep the batteries warm enough so that they would continue producing electricity. Otherwise, the electrolyte would freeze and they would lose the instrument. So this represented an absolute extreme situation in terms of the environment that they were working in. So here's some notable pieces, and we'll come back and revisit some of these in person later. Over on the left is the first piece recovered, which was recovered visually. They actually saw this down on the ice. This is a piece called the stovepipe, and it was not radioactive, detectably radioactive at all when they recovered it. But we know it's from the satellite, and I'll show you why shortly. The piece in the middle here is one of the beryllium reflectors, and when we talk about the reactor system, you'll see where it belongs. These things tended to measure around 20 to 100 Röntgen per hour, so they came down pretty hot. Over on the far right side is a piece of one of these beryllium reflectors that was known colloquially as the moose hoof, and then down at the bottom we have a piece known as the antlers. And this is some coolant piping, and this reactor used a coolant that was based on NaC, or sodium potassium alloy, to remove heat. And so these are some NaC pipes, and they would have passed through the shielding behind the reactor, after the reactor. And so this piece fell on the Thelon River near a couple guys who were out camping and doing an absolutely crazy thing that I would never do. But those guys were flown to Edmonton to be cleaned up in the wake of this episode. And then, of course, the antlers were pretty spicy, and they were removed to Pinawa, where I think they've probably been destroyed as radioactive waste at this point. So these are some of the notable pieces that were recovered, but there were lots of little tiny fragments of the reactor. Let's see here. So we'll talk just a little bit about the mission. So these were for reconnaissance from low Earth orbit, looking for ocean-going, ships. mission life 1 to 2 years, nuclear reactor power source was chosen. And at the end of life, the intended trajectory for the satellite was re-entry, except for the reactor part, which would split off and would then be chemically ejected into a higher parking orbit or storage orbit. So the reactors from most of these missions are still up there and are not going to come back for thousands of years. So they don't represent quite the same issue that Cosmos 954 did. Yeah, so this is, you know, park the reactor and then the rest can crash. That was sort of the idea. And these would last 1 to 2 years, and then they would launch another one to replace it. So,
Carl,
yeah.
are there any UN regulations about parking or used reactors?
Are there any, I think you said regulations about doing this.
Yeah, like are there any UN regulations about parking used reactors in high orbit?
You know, that's a good question, and not that I'm aware of. There are regulations about who pays for cleanup if something goes wrong. You know, they're international treaties. It's hard to call them regulations, but they're, you know, countries agreeing, you know, we will have a internal enforcement mechanism for these circumstances if something goes wrong. But as far as parking reactors, I don't think so. There's definitely a matter of courtesy when you do something like that,
right,
to not park it near where somebody else is operating.
Because I could just, I mean, like in the extreme limit, you just have like at this one altitude, just like a giant spherical shell of used reactors. I mean, this seems not really ecological.
Right. Now, the real problem with the Rorschach missions, the reactors are kind of out of the way, but the real problem with these missions is that when the reactor is ejected, there's a spray of coolant. All of its NAC basically gets released into space. And so this eventually forms a cloud of little droplets, some of which are big enough to cause damage to other things, and that also contain a lot of argon, radio argon from the potassium being irradiated. So the real problem with these from the space junk perspective today is there are these clouds of NAC droplets rolling around, and some of those have actually caused damage. So this was considered a problematic approach by people who were not the Russians, even at the time. So these drawings here show the configuration of the satellite, and there's a lot of drawings online that are not technically accurate because people had to speculate what exactly is in this thing. It's a military satellite, it was classified, but you have a forward section that contains the reactor power plant, an aft section that contains the radar payload, and if you look inside the forward section, this is made up of the reactor, its shield, and its radiator. So this is the power supply, and the reactor is at the very nose of the thing. Then there's a lithium hydride shield, and behind that is a thermal radiator that you know, rejects heat. And also the thermoelectric power supply is located behind the radiator. So anyway, that's how this thing was configured. Here's a drawing from Rosatom from a couple of years ago. They actually released some technical details on this thing finally, showing how the actual reactor plant is built. The state enterprise that built this thing is still a going concern. There are concerns about its level of staffing and the, I guess you would call the culture or, you know, just how good people feel about their work, you know, the work ethos there. But they are still designing space-based reactors, including some that are, you know, an order of magnitude more powerful than this one. And that's the Krasnaya Zvezda, or Red Star Design Bureau. So this, as I mentioned, there were about 30 of these missions, which makes this the most widely used space nuclear power plant. And you know, you could say it was pretty successful. It had a couple failures. One fell into the ocean. Nobody ever recovered anything from that one. And then Cosmos 954, which went down over Canada. But basically what you got is a fast reactor system. that is controlled via the reflector. So the reactivity control is from this beryllium on the outside of it, and it's cooled by liquid NaC, and and then you have shielding to protect the payload that is composed of lithium hydride. And so some students at Los Alamos did a nice little design study of this in the last couple of years, and I encountered their document online, and it's pretty fascinating. Most of the design information that we know about this thing does come from the one that fell in Canada, and a little bit has been released by Rosatom, but really not too much. So it's a fast reactor. It's fueled by a uranium molybdenum alloy. These are still sort of state of the art as far as fast reactor systems for difficult environments. Highly enriched uranium cooled by NaC, as I mentioned. Electric power 3 kilowatts derived from thermoelectric generators based on 100 kilowatts thermal. So not a very efficient system, but you have to pump the NaC. So a lot of your generated electricity from this power source is going to supplying the electromagnetic pumps for the NaC, and that's not included in the 3 kilowatt electric. And then reactivity control via moving beryllium cylinders, and up in the upper MCNP diagram here, you can see the cylinders are empty, and this has a K effective of 0.9. And then down below, if you put the beryllium cylinders in, you get supercritical K effective there. So that's how reactivity control was done in it. And if you go back, let's see. Hello. There it is. Okay. If you go back, here's one of these beryllium cylinders at the top of this slide. Well, this is those beryllium cylinders. There's 6 of them mounted azimuthally around the reactor. So why is this still relevant today? Well, there are people still living in the Northwest Territories who will not go to certain places, an example being Tomato Island, because they have heard that it is contaminated, that it's radioactive there. They think people have found things there. Scientific observers have not found such things, but that does not wipe away the stigma of somebody saying, well, we think things fell there, and who knows. So people still are still being impacted by this, whether it is psychologically or whether it is there are still things out there we know, and it's just a question of where they are and what they've done in the environment since. It's also true that right now there are more powerful space nuclear power systems being developed and tested. We hear about them from time to time, not always in a good light. There was an air-breathing nuclear reactor thermal propulsion system that was tested at Nyonovska in northern Russia about a year and a half, 2 years, about a year and a half ago, I guess, that blew up and killed some people and left a trail of contamination. We also know that the Russians are working on a more powerful 2 to 3 megawatt thermal Earth orbiting satellite that's meant to last 5 to 10 years. And it's a sort of different technology from the BES-5 reactor, but this is under development now, and obviously would have a higher core inventory and would be Earth orbiting. So many opportunities for it to deorbit over places that matter. And then finally, this is the only space nuclear reactor to re-enter the atmosphere over land and provide an opportunity to study what happens. The US has worked on space nuclear power stuff. We've flown nuclear reactors, but and the Soviet Union, of course, and Russia have done a lot of this, but Cosmos 954 is the only one that that gives us that legacy of actually having failed in that manner. So, yeah, question.
Do you know why the higher power is needed for the satellites?
Oh my goodness. Well, people are speculating. It's military hardware, and why do you need a lot of power up there? Well, it's because you need to support high bandwidth communications, or it's because you need to run radars. So this may be a 40-year-old concept, but it's the fundamental aspects of it are still the same. High-speed ground data links and radars, take a lot of RF power to run, and where are you going to get that power? Well, you can get it with solar panels, but you know, at the expense of other aspects of the design. So yeah, you know, beyond that, I've seen a lot of people trying to speculate about what exactly Russia wants to run with that 2 megawatt thermal system that they're testing right now. And I think it's just, you know, the military people can speculate on that, and I'm not sure I can do a better job. So I got to, I got a crazy opportunity this summer, and for many reasons, I thought long and hard about doing this, but because I am who I am, I went and did it anyway. So a guy calls me from Vice Television and says, you know, that space nuclear reactor that, you know, fell in Canada? I'm like, yeah. And he says, well, you know, I know you like to go look for radioactive stuff. Do you want to come look for this thing? And, you know, hell yeah, of course I do. I mean, the thing is, it's like looking for a needle in a haystack. When Operation Morning Light was going on, they had the benefit of having all of these short-lived fission products, and the stuff had fallen on mostly a frozen lake, so it was easily accessible, and, you know, hadn't had 40 years of the environment to degrade it. So they had an easy job. 40 years later, that job's almost impossibly hard. And I told them up front, you know, I don't think we're finding pieces of this thing today, but would I like to try? Absolutely. I think I'm, you know, one of the best prepared folks to do it. And thank you for calling. So it became a reality. You know, a lot of these TV pitches don't. They're kind of crazy, and they cost money, and producers, you know, will green light 1 out of every 100 of them or something. But Vice News decided to green light this thing, and so we put together our stuff and went and did it. That photo I took there is of incidentally, another radiation effect, the Aurora Borealis. I was lucky enough to be in quarantine at the hotel in Yellowknife during one night when there was a geomagnetic storm, and so I took a photo of the aurora, which here in New Mexico, very unlikely any of us will see. But yeah, I had to follow Northwest Territories guidance on quarantining, so we were quarantined, and by that I mean we couldn't leave the hotel room. We were doing our laundry individually in our room, we were eating in our room, and so forth. So 2 weeks of that, and then 1 week of hunting for pieces of the nuclear reactor. And Vice News decided to sponsor this and film it, and so they brought out a TV crew that was half US, half Canadian. And I'll entice you here. I'll say we found radioactive stuff. So there's some fun to be had later on. We'll talk about that. So how do you plan an expedition like this? You have a week, you want to maximize your chances of finding this needle in a haystack. So I decided that our search strategy was going to be simply cover as much ground as possible and look near where other debris had already fallen. So if you go back through the slide set, you'll see that 600-kilometer long trajectory of debris. Well, I looked for where the highest density of large debris was. And over here on the right-hand side of this slide, you can see an example of what that looks like with a resolution of about, this is about 1 mile between these two blue points right here. So that's what I mean by high density area. So we're going to cover ground. We're going to use mostly scintillation detectors, and we'll also have some alpha, beta, gamma sensitive, you know, stuff. We'll also have some radioisotope identifiers, and these come in real handy, and I'll show you why shortly. How do we get to this place? Well, we can spend 2 days on a boat going there. That takes forever. We can hire a float plane, which takes about 45 minutes and is a better choice ultimately. And then we can use other boats to get around the Utsingi Peninsula here and look at some other spots. This little spot up at the top of the picture is where the hottest piece of the whole thing was found. So we, of course, want to go out to that point just in this area and, you know, see if we can find anything else. So after we decide on how we're going to get out here, we decide on, you know, we use satellite imagery to find places that are good landing zones for the airplane. These have to be sort of sheltered areas with a beach where the plane's pontoons can back up to. And most of Ethan Island and these other islands it's a very sheer rocky shore, and so unsuitable for parking the airplane. So this took quite some time. We had to get the high resolution sat imagery to locate where the plane could land. And luckily we got, our first most promising landing zone ended up being a good one for the airplane. So they circled a couple times and gave us the thumbs up, and we landed there. It's a twin otter airplane, turbine airplane, that's very common in this part of Canada. And this is what the terrain looks like. It is very wet and very rocky. And in places that are further inland, there are trees. Bears can get around this no problem. Anyway, so we were dropped off on the north end of Ethan Island, where we wanted to be, landing zone number 1, in good weather. And there's all our camping gear and detection instruments and whatnot and food, and the airplane takes off, and there we are for a week or thereabouts. So a little background on the environment up here. Obviously we're here in the summer, and that is huge. That is enormously beneficial. In the winter it's 40 below. That's 40 centigrade, minus 40 centigrade, and minus 40 Fahrenheit. But in the summer we have weather in the 50s to 70s, and this terrain is very, very rugged. It's easy to break an ankle in there. Bears are abundant. We have grizzlies, we have black bears. We saw 2 bears. We had a bear come through the camp at 5 a.m. one morning. And we had to hire a licensed bear guide who was part of our crew and carried a shotgun and bear repelling tools of various kinds. Wolves are out here, moose are out here, and are considered the most dangerous animal because they're territorial and unpredictable and weigh thousands of pounds. And the mosquitoes are just insane. There are thousands of these things around your head at any given time, and you just have to learn to ignore them. And so this is the summer. This is the nice season out on Ethan Island, and absolutely barbaric in some respects. So we went out and looked at, as I mentioned, we had a search strategy, and this spot here I went to not because we would find anything because it's over open water, but simply because it is where the hottest piece was found. And so we went out within a few meters of where that spot was, and just ceremonially caught ourselves a fish for lunch. And by the way, this was lunch most days. We'd get a lake trout, which usually took all of about 2 minutes. We would cast out a lure, and almost before it hit the water, there'd be a fish biting it. And some of these fish are like 20 pounds. One fish is suitable to feed everybody. And so anyway, we went, this was off Utsingi Peninsula where the hottest piece of the reactor was, and we caught a fish for lunch, which was not radioactive. Some of the people were worried about that, so I had to demonstrate, the only thing we see off the fish is potassium-40. So we did get a hit. I mentioned this. We, in fact, were within a few meters of where a chunk was recovered, an Operation Morning Light. And of course, we were extremely ecstatic to have a hit, and I started digging for it. And about 2 feet down, I stopped and I said, we need to put the RID in there, because at this point we don't know if it's natural or synthetic, and if it's reactor material, what we expect to find. Well, fission products like, possibly some cesium-137, reactor fuel materials, highly enriched uranium. So, and if it's natural, what do I expect to find? Well, the decay daughters of uranium and thorium. So, moment of truth. And, if we actually wanted to dig up what's here and didn't know what it was, didn't have the benefit of the RID, we would be digging on this thing for, who knows how long. But this is the value of the RID. We can put it in there and know what we're looking at, why we got the hit in that particular spot. So here is our gamma spectrum. You can see that we have a number of peaks. This is a log scale. It's a sodium iodide detector, kindly loaned to us by Berkeley Nucleonics to do this. We can see that it has identified the nuclide as radium-226 with a confidence level of 100%, and it gives us a dose rate where the detector is. And at this point I said, you know, we can stop digging for this one because it's a natural occurrence. So this happened to be a pretty good hot hit. And so this is one of the complexities of looking for something like this now. You have environmental sources of radioactivity, including this one, which is, you know, you could mine this deposit actually. It's got enough uranium in it. It's interesting from the mineral value point of view. But yeah, so we found something. It just happened to be naturally occurring. So I want to conclude the slide set before I go to the little video by showing you we did visit pieces of Cosmos 954. We did go to the Northern Heritage Center in Yellowknife, which has, I was surprised, they actually have 3 pieces of actually 4 pieces of this the satellite, not the reactor. They're not allowed to keep anything radioactive, but this is a piece of the satellite. So I'm going to let's see. Am I still? Can you still see me? Am I still here? Yeah. Okay. Yeah, I think that's me. Okay. So having shown you that, I want to go ahead and show you a little video clip, and I hope the bandwidth will support it, but let's give this a try and we'll talk about the pieces they have at the Northern Heritage Center, and then there'll be some time for questions. So let's get rid of that, share screen. We're gonna go to advanced, or no, I'm gonna go to advanced. Wait, what? Okay. Basic, optimize screen sharing for video clip. Okay. And now I need to open my video. Hang on one sec. So I'm here. Okay. Oops. Sorry, it's a figuring this out as I go here. Here we go. Share screen and optimize for video clip. And where is my video clip? There it is. Okay. Full screen. Can people see this? Okay, I'm hitting play. Hopefully this works. So I'm here at the Prince of Wales Northern Heritage Museum in Yellowknife, Northwest Territories in Canada. This is a piece of a Soviet reconnaissance satellite, Cosmos 954, that was powered by a 100 kilowatt enriched uranium nuclear reactor. And this component that the museum is fortunate to have was said to be non-radioactive when it was recovered. It's called the stovepipe. It was identified from the air visually, and it is, as the description states, pretty much just a piece of pipe. And its function in the satellite is kind of a mystery. One would have to study the design of the Roarsat system pretty carefully to see where this came from, I think. But it's a fascinating piece. There's no doubt about its provenance as part of the satellite because it actually has some Cyrillic lettering down at the bottom, and there's a sort of a cryptic number. They also have 3 other pieces of the Cosmos 954 system. Again, when we put our detectors on them, we didn't see a lot of radioactivity, but you know, a more detailed analysis might show some. This piece looks like it has some sort of fiberglass composition, and of course it's charred from the heat of re-entry. This piece over here has a somewhat similar sort of fibrous texture to it, and again, one can only speculate, I guess, where these pieces came from in the satellite system. That would take some further analysis. But they were not close to the nuclear reactor, because otherwise they would be radioactive from activation or contaminated by nuclear fuel. And this piece appears to be a metallic gasket or flange of some type. And again, it shows significant degradation from the process of re-entry. But this is just a fascinating picture of the space application of nuclear power. And this particular satellite fell over the remote part of the Northwest Territories occupied by the Dene people. And it was really sort of a collision course between the cultures that use these nuclear power systems in space, namely the United States and the Soviet Union in the context of the Cold War, and the people that had been on this land for a very long period of time and did not have a word to describe nuclear radiation. So when the recovery effort happened, there was a lot of confusion, miscommunication, and perhaps challenges dealing with how to explain what this object was and why people in moon suits were going to collect pieces of it off of the ice of the Great Slave Lake. I'm here with Scott Marston, who is, well, Scott, why don't you tell us your role here at the museum and explain a little bit about what the museum does with objects like this.
Yeah, so I'm the curator of museum collections for the Prince of Wales Northern Heritage Centre in Illinois, Northwest Territories, Canada, and we collect objects that tell the story of the Northwest Territories. So this object, as you said in your preamble, is an object that's from a reconnaissance satellite that crashed in the Northwest Territories in 1978, and then upon its arrival in the Northwest Territories, it became part of the narrative of the Northwest Territories, and that's part of our job here in the collections program, is to collect objects that are rare, that are historic, and then contain information about historic events. So this obviously was an historic event. The Canadian government came and looked for materials, and there was an engagement with the USSR and engagement with the local indigenous communities here, and so it becomes part of the history of the Northwest Territories. And it's essentially one of our primary functions, is to help tell those stories. And here you are, recording this incredible object, and we're telling the story.
Yeah, well, thank you very much, Scott.
I'm happy to help you.
So I've also got Taylor Wilson, a nuclear scientist from Reno, Nevada, with us. And Taylor, what equipment did we bring, and what measurements did we take, and what are sort of what's our understanding as of right now from those measurements?
Yeah, so we have a couple instruments here. We've got a alpha, beta, gamma Geiger-Muller detector, so that'll tell us if there's any, residual contamination, which we didn't find. It's pretty much background levels. So take a look here. We can see what the pieces look like. As you can see, it's not showing up much on the Pancake GM.
And this would detect things like perhaps strontium-90, some long-lived beta-emitting fission product.
Sure, or nuclear fuel, highly enriched uranium, plutonium, cesium-137. But it doesn't seem like there's much here.
But generally, a surface measurement with that particular tool. If there's something on the surface and it's emitting charged particle radiation, that is a good tool to use to measure that. And we're not seeing anything that is detectably or noticeably above background. So what else did we bring here?
So we've also got a couple of radioisotope identifiers. This one is my personal unit. It's got a pretty large sodium iodide scintillator, so it's very efficient at detecting gamma rays. And if we hit identify there, we can get a gamma spectrum. So just like an optical spectrometer breaks down the wavelengths, the colors of light, this does the same thing for gamma photons. And you can see the spectrum there. And obviously, the most prominent things that shows up is this peak at about 1.4 MeV. But that is naturally occurring. That's potassium 40, which is in all the rocks in our human bodies. And that is not a signature of the satellite. But if there were fission products or activation products from the reactor itself, we would be able to see that in the spectrum. And so we'll have to go back to the lab and analyze these later. Maybe there's something in there from the satellite, some signature, some remnant of the nuclear reactor.
That was the other radioisotope identifier in the background. Sometimes it throws a little alarm for no particular reason, or maybe there's another nuclear satellite making an unexpected reentry. So both of these are manufactured by Berkeley Nucleonics, and the one that Taylor brought is a much larger detector, so it's more sensitive, but it's an older model. And the other one there that they kindly loaned us is a new top-of-the-flight ruggedized model. We just had this out in the field looking for pieces of this satellite. Smaller detector, but it has some portability and weather, sealing advantages, I guess. So that's really a suite of instrumentation we brought here. Based on just our cursory look at these field instruments and the measurements they make, I would not say that we're seeing a great excess of radioactivity from these pieces, which no doubt is encouraging for the folks who work here. And yeah, but for those of us who live and breathe nuclear technology and nuclear forensics, of course, we want to find radioactive material, and when we do, it tells a story that we interpret through the tools and techniques of nuclear forensics. And so we may not have a story to tell other than we could not detect anything. So, but as Taylor said, we'll have to return to a laboratory setting to evaluate these spectra more fully, look at the statistics of the measurement, and basically see if our field interpretations are in line. So, fascinating piece of history. This is relevant today because Russia is still working on derivatives of this technology, except 10 times more powerful. They would like to launch a 1 megawatt nuclear reactor that's based on the same sort of enriched uranium with a liquid metal cooling system and thermoelectric. Or
all right, so I'm gonna quit that deal right now, and if there are questions, I would be happy to entertain them. And so, because this was sponsored and filmed by Vice Television, they're producing a TV episode about it, and I only know what its working title is. I don't know who the buyer is for it. They wouldn't do it without a buyer, but I don't know if Netflix, Amazon, or some other streamer is gonna distribute it. So all that's very premature, but I had fun. We ate a lot of fish. We got bit to death by mosquitoes. We did find radioactive stuff, just didn't happen to be satellite parts. And we did go and see satellite parts that had already been found. If somebody wants to go look for this sort of thing today, the answer is it's going to be extremely difficult to find things. There is no detector in the world that is good enough to be able to tell you what is what's still going to remain 40 years later. So one of the things that we had to contend with is, what exactly is in the fuel today? Well, there's not a lot of cesium-137 in it because as the system re-entered the atmosphere, the temperature was high enough that virtually anything volatile, which includes cesium, boiled off. So the cesium-137 made it almost exclusively into the atmosphere, and we are bereft of one of our long-lived high gamma yield fission products in most of what remains today. There's only the question of how much relative to what else might be radioactive there. So one of the saving graces of the atmosphere for space-based nuclear power plants that re-enter is that the re-entry process cleans out a lot of the damaging stuff, and then you just get a cloud of radionuclides that persists in the far reaches of the upper atmosphere for years or decades, but you're not getting localized concerns on the ground. So that's something that I'll mention as far as, you know, what happens to the core inventory as the thing deorbits. But this is definitely a space to watch because there's current developments afoot. There are air-breathing nuclear thermal propulsion systems and space-based low Earth orbit high-power systems that we talked about that are going to be launched. In terms of what the U.S. is doing, there's interest in space nuclear power for some missions that might be a decade away, some scientific missions. We just launched another plutonium RTG to Mars as part of the Perseverance rover. And that's obviously not a reactor, but still it's a concerning amount inventory of radioactive material. So these are issues that you have to be aware of, and you know, the large parts of the entire world are stakeholders in projects that involve space nuclear power, especially Earth orbiting systems, because they could come down just about anywhere. So on that note, I will stop blathering, and with a few minutes remaining, if there's any questions, I'll entertain them.
I have a question.
Yeah.
Yeah. So, is there some kind of strategy that like the Soviets or even us for Earth orbiting nuclear powered stuff? So like, you know, they're launching 90% enriched uranium into space. Do they have a plan, or are they just expecting it to just remain in orbit forever?
Yeah, well, nothing stays in orbit forever, but it's a question of sort of when is it safe for those items to come back down, and the consideration has always been defined by treaties that make the onus on cleanup belong to the person who launched the thing. And so under this treaty, the Canadian government sued the Soviet Union for $6 million, I believe, or maybe it was, I think it might have been $8 million, something like that, for the cost of cleanup. A lot's happened in 40 years. Now this would be, you know, probably $100 million. But the USSR actually paid. They didn't pay the entire bill. They paid half of it in true Russian style. I think they paid $4 million and said, you know, that's it. If we had been allowed to clean it up ourselves, we could have done it for less. But so the thing to be aware of is there are treaty obligations to clean up the mess that you make, and so you basically have to think of what is the worst mess that this thing could make if it is disposed of, you know, according to our plan, and how much, you know, would we have to pay, you know, as a contingency if that happened. I think that's pretty much how people think about these things. And as far as the accident probability, here in the United States, we have environmental impact assessments. And so, for example, the Perseverance flight that left from Cape Canaveral, you can look up the environmental impact assessment that NASA did for that project, and there's something like a I think they speculate about 0.5% chance of failure at launch, and a 0.1% chance of high altitude failure. So they put those kinds of numbers on it, and then as far as actual dose assessment, they have some sort of health physics people who do that. But you know, the issue is definitely not negligible. It's a big cause for concern in the design of a mission like this, because you know, space travel is not all that reliable compared to, you know, other means of moving things around. vehicles fail relatively frequently. It's just the most likely time for failure is during launch. And if it's a reactor, for instance, if it's highly enriched uranium, it's going to stay subcritical and just be dispersed. And then you have a much smaller problem than if the reactor has been at power for a number of months or years in flight, and then it deorbits. It's very qualitatively a very different problem.
Okay,
If you
thank you.
had found something, what would the procedure then kick in? Like, say you found, like, you know, a fuel rod or something crazy like that. What do you do now, sitting there in the wilderness with a fuel rod?
Well, I mean, my instinct is to try to retain control of that item and bring it back for, you know, further analysis. Canada's a lot stricter than the US is about radioactive stuff. So even things like naturally occurring radioactive material, minerals and so forth, are regulated differently in Canada than they are in the US. And so, I mean, I figured the chance of that happening was so small that I didn't really even consider putting some sort of procedural contingency in place for that occurrence. I figured if that occurred, if we found such a thing, we might just have to leave it in the custody of you know, the Canadian military or environmental control people. You know, ultimately, I'd like to have custody of something like that, but that would involve, you know, the export of highly enriched uranium from Canada and the import of highly enriched uranium into the United States. I mean, presuming we're a fuel rod, the regulatory landscape is not not conducive to doing that. That's a headache upon a headache. So I didn't even go down that route and ultimately didn't need to. And yes, I would love to find a fuel rod. I know there's stuff out there. It's just a lot of it is probably at the bottom of Great Slave Lake because there's not, you know, it's fallen through the ice. All righty. Well, anything else?
So do you know how the satellites go up? Is it like on a chemical rocket?
Yes. Yep. They're just put on standard, you know, 2-stage missiles, basically. You know,
Yeah, I was a little curious as far as the prospect of landing them. So I guess they don't have self-propulsion to go up and then back down for like a controlled landing, and they aren't designed to have shielding around the reactor for being in atmosphere.
no, absolutely not. They're the reactor is meant to be jettisoned another 1,000 kilometers up in orbit, and then it just stays there for, you know, thousands of years. And the rest of it, you know, it's uneconomical to have that much fuel on it for the whole thing to do that. So they just, the radar part of it, they just deorbit and it burns up. And so there were about, I think there were 33 of these things, and they've all, at this point, all of them except for, I think there are 30, well, there would be probably 31 reactors still up there.
But in orbit?
Yep, in orbit. And, you know, we collectively know where they are. We know where they are. It's just, you know, there's nothing really to be done with them. They're in a safe place. And as long as something crazy doesn't happen and one of them, you know, breaks apart or something and a piece ends up on a trajectory headed back towards Earth, we probably don't have a whole lot to worry about from these things.
Do you know of any particular instance where that liquid NAC caused trouble for anything else up there?
Yeah, so I've read about the NAC causing damage. I hate to be as lazy as to throw a Google search up here, but let me go ahead and do that. Let's see, where is it? I did put this up here. I did put it up here. It is here. There it is. Yeah, so there's some fun stuff here for sure. Effects of the Rorschach NAC drops on the long-term evolution of the space debris population. This is from 1997. Looks like a interesting enough paper. It doesn't talk about specific damage. Here's something else. The NAC population, a 2019 status, and this is a paper out of the Johnson Space Center. So I guess they say, yeah, let's see. Brief history of NAC sources. So they go through, all of these Cosmos satellites that produce NAC. News sources, well, there's a couple other reactors, the Topaz reactors, which were a evolution of the reactor in the Rorschach. Anyway, it looks like it's a subject of considerable current interest. I don't know if there's any particular damage that this has caused, though. I just, yeah, I'm aware it's an issue.
Cool. So if there aren't any more questions, we can wrap this meeting up. Thank you all for attending. Very cool. I think within the next 2 weeks, INMM is going to be back, and I believe I am the next speaker. So I don't know the topic as of yet, but I'll come up with something interesting, and probably not as interesting as this, but it'll still be really cool. So again, thank you all for attending, and yeah, please use the Discord if you haven't already. It's a very cool tool that we're trying to get more engagement on. So cool. See everyone around in the digital space.